What I am trying to present you today will not be a lecture. It will be rather a demonstration or an experiment. And this experiment or demonstration, or whatever you like to call it, has the aim to present to you my attitude to teaching. You see, it is not a method, it is not a system. Teaching is not a science, it is an art. You cannot put it really in a system. But you may have an attitude to it. This attitude cannot be easily described in words, more in acts, and I will show you that afterwards if I can. But I can tell you a few slogans. Let me put my first point in the question and answer form. What is teaching? In my opinion, teaching is giving opportunity to the students to discover things by themselves. Not the teacher should tell the things to the students. If they wish to learn it really, they have to discover it. A second point. First guess, then prove. All great discoveries were made in this time. The discoveries in the mind of Archimedes or Gauss or Newton were conceived this way, or anyhow some of the important ones. And any kid in the classroom finds things this way. First guess, then prove. My third point is a straightforward application of this point to mathematics. Mathematics seems to consist of proofs, but it's not quite so. Finished mathematics consists of proofs, but mathematics in the making consists of guesses.
The academic ideal in mathematics, as well as other disciplines, is that of the scholar-teacher, the person who can contribute notably to the world's store of knowledge and understanding, and who can also make others in their teaching effectiveness. One man is acknowledged to be preeminent, to be the paradigm, the archetype and model for us all. This exemplar is Georg Polya. Much of Polya's academic life was spent in Switzerland after his education in Budapest. He came to the United States and joined the Stanford faculty in 1942. He holds a number of honorary degrees and has written many books and some 220 articles, most of them the fruits of his imaginative mathematical research. His contributions to the combined fields of mathematics and mathematics education are unequaled. The demonstration which you're about to see is truly unrehearsed and spontaneous. It illustrates his extraordinary, his uncanny ability to stimulate a group to guess intelligently, to make reasonable conjectures, a process which is essential to mathematical discovery.
Ladies and gentlemen, I don't wish to give you a lecture, you see. But I wish to teach you about guessing. See, it's a very important part in life to be a good guesser. See, it's a very important part in mathematics. You wonder a little how, because if anywhere, so in mathematics you have proofs, and only that is valid in mathematics what is proved. What is there the part of guessing? Yes, there is a part. Mathematics, when it is finished, complete, all done, then it consists of proofs. But when it is discovered, it always starts with a guess. And I wish to give you a real experience of it. So I don't will give you a lecture, but we play together a guessing game. See, you should find out from your own experience what is reasonable guessing. Not wild guessing, that can anybody. Wild guess is that you don't have to learn. Anybody is ready with a wild guess. The less you know, the easier to make a wild guess. But an educated guessing, a reasonable guessing, that is something else. That should be learned. And the mathematics class is a good opportunity to learn it. So we play together a guessing game. This, as any other game, has rules, but the rules are very simple. And there are just two rules. One for those people who will know already my question. I hope there are very few. But if you know already my question, if you know already my problem, don't answer my questions. That would be unfair. If you know already the answer in advance, it wouldn't be guessing, and you would spoil the fun of all of us. So don't do that. However, if you don't know the answer to my question, then don't hold back. See, don't be bashful, but guess. Of course, your guess may be wrong, but that's one of the points in the art of guessing. Even a wrong guess is helpful. The wrong guess leads you to a better guess, and that's to a still better guess, and finally you get the truth. Well, that was enough introduction. Let us go into the matter. So I give you a problem to guess. It will be really a problem of solid geometry, but you know as solid geometry, not much is there to know. For instance, everybody knows what is a plane. A plane is very flat. The top of his desk. This is part of a plane, or approximately. The better it's made, the smoother it is, the flatter it is, the better it resembles to the ideal plane of mathematics. But the ideal plane of mathematics goes over in all directions. It is infinite. So you know what is a plane. It is flat and infinite. Now, my problem is about planes. Several of them, and to tell the whole story about 5 planes. So you imagine 5 planes. So if you cut, so that is 1 plane, 2 planes, 3, 4, 5 planes. Now these 5 planes cut the space in many parts, or divisions, or compartments, or whatever you call it, and that's just the question. How many parts? This is my question, or almost. There is something to be added, but I wait till you find it out by yourself. But you understand it. You imagine a big piece of cheese, some cheese you like. It may be green cheese, it may be Swiss cheese, whatever you like, and then you cut it once, twice, 3, 4, 5 times, very sharp in a plane. There are lots of many pieces, and you have to guess how many. Who is ready with a guess? Don't be bashful. Go ahead. Yes, say something.
25.
25. Grand. How did you get that?
I multiplied 5 times 5.
5 times 5. That's an idea. There is some idea. Good. Anybody ready for another guess? Yes, please.
32.
32. Oh. You have something behind your... Oh, 32. It's interesting. So, quite big numbers. Still another guess? Well, that's enough to start with. Can both guesses be correct? Can both guesses be correct?
Yes.
Yes. Oh, that's interesting. I didn't expect this answer. But you may be right, who knows? Now, I thought, all right. Any other guess? Any other question? Yes, please.
I'd say 10 spaces.
10 spaces. 10. So many. You have 10. Well, we shall see who is right. But you see, there is another point. You see, guessing, that's the important beginning of solving any problem. And the real problem is difficult. A real problem, you cannot do it right away, otherwise it would be a problem. It belongs to the idea of a problem that there is some difficulty. So if you cannot do a problem, what to do? Just wait for an idea? No. The right thing is try to imagine some easier problem which could prepare you for the problem. Some easier problem which could help. And in this case, it is not very difficult to imagine. You should be suspicious in life, you see. So if I ask you 5 planes, then you should have asked yourself, why does he ask just 5? Why not 4? Why not 6? So what would you ask? Yes.
I guess you mean how many planes do, say, 3 planes,
3
spaces
planes.
do 3 cover?
Good. Or what do you say?
Well, the simplest model would be 2 planes, I would guess.
2. Is that the simplest?
Well, not
One plane. Oh, yes. So much trouble to find the simplest. 1. Yes, that is the... You see, but it is so, in mathematics, often the simplest is the best. So, here is... Here is for you 1 plane. Oh, you tell me that is just 1 line on the blackboard. Yes, it is true, but I mean it in the following way, you see. This line on the blackboard is the intersection of the blackboard with a plane, you see. By this plane I am showing you with a horizontal plane. In this horizontal plane could be the surface of quiet water, of a reflecting pond. And there is nothing else in the world, just this surface, and over it air, under it water. So how many parts?
2.
2. Good. Please,
I'd
what
like
is
to add 12 to the guess.
12. Oh, yes, good, certainly. Guesses are always accepted. 12. So, but in this case there are just 2 parts. Is that clear? You see, but in mathematics that is an advantage. First of all, you can make yourself completely clear the simplest cases, and they are useful. So in order not to forget it, I wish to note it down. So I have just 1 dividing plane. It is long to write down divide. I just write the end. Dividing plane. And there is just 1 dividing plane, then the number of parts is exactly 2. Good. This was 1 plane. So what is the next case? After 1, what comes after 1? That's good, so good, so great kids and can already count to good, too. That's good. So, here are. That is any plane thrown at random, here. Oh, you see, that's not a plane, just a line. Yes, but I mean it so. You see, this line is the intersection of the plane of the blackboard with, you see, with such a plane. So you have two planes, 1, 2. And how many parts do you see? 4. 4. Oh, please, answer loud, nicely, you see. You can shout much louder. Okay, so you have 2 planes, you have 4 parts. Good. Now, what about 3 planes? Well, I will tell you once. Yes, please, you have.
Could I ask you a question? If the
Yes,
planes
please,
were,
do ask a question.
if the planes were parallel, would it still divide them into
Very
4?
good question. That's a good question. I have waited just for your question. Now, that's a very good question. If all the planes are parallel, 1, 2, 3, 4, 5, then it is no problem. If all 5 planes are parallel, little imagination, like that, then there are how many parts? 6. Well, then the whole problem would be over. This cannot be the question. Very good. That I wanted you bring it out. Yes, my question was incompletely stated. And that was so intentional, you see, because problems in life, real and even in science, they are often incompletely stated. You have to find out what the real question is. So my real question is, you see, that planes should not be parallel, or should not all pass through at the same point. They should be taken at random. Here is one plane. Here, let us see the plane of the... And then you wish to make another plane. Well, how shall I make another plane? You see, so you could make on a piece of wood, you could make 2 planes. Well, it's pretty difficult to make a good plane surface on a piece of wood with a planer. And when you made one, then the second should be parallel. Do you think you will ever succeed? Maybe it will be good enough for the piece of wood, you see, you wouldn't see the difference. But if both were produced far enough, very like they would have a little inclination, and far enough they would do what they would. If they are not parallel, then they do intersect. So you see, if the planes are taken at random, then no 2 will be parallel, or no 3 will pass through the same line. You see, that is almost impossible. Well, I hope you have a sound idea about it. So this was 2 planes are taken at random. You feel happier about your question?
Yes.
Good. That's a very good question. Now, look here. So, 1 plane, 2 planes. How many parts?
4.
4. Good. Answer with conviction. 4. Good. Oh, we did it already. Now 3 planes. 3 planes. It would be a bad idea to put it just right through. That would be a bad idea. Or just... no. Oh, I know. The blackboard, that is the 3rd plane. Good? It's good enough for a 3rd plane. Then look here. So there are the 2 planes indicated by the lines and the blackboard. There are some of the parts are in the room in front of the blackboard. How many such?
4.
Good. Some other parts are outside the room behind the blackboard. How many such?
4.
So altogether how many?
8.
Good, 8. Now, look here, perhaps the most important point. You understood now the problem, and I have so little space, I must erase it. But here will come really the most important thing. I wish to draw your attention to the most important points in reasonable guessing. If we had more time, I would introduce each much slower, but we have little time. So I tell you right away one important point in reasonable guessing, to think of extreme cases. For instance, in our case, such an extreme case would be that there is no dividing plane. Number of dividing planes is 0. Well, then there is not divided, then there is just one space. Good. Now let me come to the next case. We have 4 dividing planes. Try to guess it. 4 dividing planes. How many parts? Oh, so many hands up. You tell it.
16.
16. Who seconds the motion? Ooh, everybody. Good. So, 60. Well, I must tell you, that is a reasonable guess, you see. And that is now an opportunity to tell you the difference between a wild guess and a reasonable guess. A wild guess comes just out of the blue, out of nothing, you see. But a reasonable guess is based on something. For instance, this guess, 16, was based on observation. Before guessing 16, you observe the numbers 1, 2, 4, 8. Well, what did you observe? What observation? What did you observe? Well, you did several. Well,
They seem to be in powers of 2.
there are powers of 2. This is the zeroth power, the first, the second, the third. Or each is the double of the foregoing powers of 2. Okay, so you observed a pattern, a regularity, a law pattern, law, regularity, or whatever. You can call it with various names. You observe that. And there is one more point. Perhaps you did not pay attention to it, but it is very important. After having observed this pattern, you had some courage to say, and so on. Or you didn't say it. You just thought it. Or you didn't think it even. But I wish to point out that belongs to it. You see, and so on. It will go on like that. It is true not only in the cases observed, but in all the other cases. So there is a step of generalization. So we got reality 16 in a reasonable way of guessing. We observed, we found a pattern, and we said, and so on. It will go on like this. We made a generalization. That's a very important, you see, I wish to point out to you, that is very important. You hear all the time about that, you see. This is important in all the sciences. How do you call that? When you get a generalization starting from observation, observing a law and generalize it, that has a name.
Prediction.
Yes. How do you?
Inductive thinking?
Induction, that's right. Our science is inductive. It is, all our knowledge was obtained in this way, well, with some unavoidable criticism. So that is, there are some essential points about induction. So, I must admit, it is a reasonable guess. But is it proved? Is 16 certain or not? Yes or no?
No.
No. Cannot you answer with more conviction, louder? No. Now, good. So I put a query after the 16. It is doubtful. Now you see what is very important in reasonable guessing. You guess, and you shouldn't hold back. That's not good. You can guess. What you should not do, that you believe your own guesses. See? Oh, you believe in it a little, otherwise you wouldn't have guessed it. And that is sound. That's healthy. But believe completely what you guessed, well, that is the standpoint of savages, not of educated people. So you doubt it. And that's not enough. You have to doubt it austerly. Test your guesses. You have to test your guess. You have to check it. You see, your guess was a prediction. You see, your guess was a prediction. You predicted if I draw 4 planes at random, then there will be 16 pieces of space. You predicted that. Now, is that so? Guess it. By the way, I will tell you, it is not very easy to imagine 4 planes at random in space. Except one point, something remarkable happens. That we can understand a little by the analogy of the plane. Analogy is another important point in guessing. You see, I discussed division of space by planes. Space divided by planes. But really simple, and I draw it, division of a plane by straight lines. For instance, if I divide the plane by just one straight line, then how many parts are in the plane?
2.
2. No figure. They have even names. They call them, there are 2 half planes. Well, that's what you wanted to say. Yes. There are 2 half planes. Good. So, let us know that. Plane divided by lines. If you divide it by one line, there are 2 half planes. If you divide it by 2 lines on the blackboard, how many parts are there? 4. May I direct your attention to that all 4 parts are infinite, you see. It is not bounded. You can go away in this part as far as you wish from the point of intersection. All 4 parts are infinite. But if you introduce a 3rd line, just at random, in any position, like that, you see, then something happens. Then there is one division of space more interesting than the others. It is bounded from all sides. It is finite. How do you call this part? What is that? You don't know that? Yes, you know it. It is a triangle. So if you introduce 3 lines, then you introduce a triangle. I foresaw that will be some difficulty. So here I show you the same figure again. By introducing 3 lines, somewhat different, you get a triangle, a finite part. And in space, if you introduced a 4th plane, then something similar happens. You get a finite body, you see. 4 planes, they include a finite. What is solid by 4 planes between 4 faces. How do you? So that's the remarkable thing that happens. So there is the tetrahedron. So if you introduce 4 planes, you get a finite part of space. That is the new thing that happens. And now, so after that it is easier to recall, it is easier to visualize the whole situation. Of course, these planes, here is the tetrahedron space, but I have to make a picture because these faces go to infinity. You see, They still cut the space in many parts. One of them finite, the other go to infinity. And how many should there be? What did you say? How many should there be? Now stick to your guns. Say what you did before. Repeat it. 16. That's it. 16. Now, all right, we shall see. Can you just by looking at it count them? Can you?
15.
How many?
15.
How did you count it so quickly? Are you sure that you counted it right? You see, you can make mistake in two ways. There is some parts you forgot. Some parts you may get it counted twice, but you counted 15.
Mm-hmm.
Could you explain us how?
First I counted the tetrahedron, and then you've drawn small tetrahedrons at the vertex of each of those. There's one for each of those. Then there would be one for each edge of the tetrahedron.
Oh, yes. Well, he is very clever. But, well, very good. But did the others follow? Well, to make it, yes, I think he is right, you see. It seems to me that he is right. I don't know, of course, but it seems to me he is right. But in order that you follow, you see, you can do it by analogy. Consider first the similar case in the plane. How many, if you have here 3 lines in the plane, there are how many parts? Now, just look at it. It's not difficult. Loud, please, you say. 7, yes. Now, you can count these 7 parts in various ways. One way of counting is so finite part is just 1. This is the most interesting. This is the triangle. Fine. The others are infinite. And they are around it. You see, around. So I can count it easily. I put my finger here and I start counting. 1, 2, 3, 4, 5, 6. 1 and 6 make 7. Yes, that's good, but not good enough. Because this I cannot quite imitate in space. Also in space, all the parts are around it, but don't surround it in exactly the same way. You see, they don't surround it exactly the same way. So we have to count it in a more sophisticated manner. And I will tell you how. There are really 2 different kinds of parts, you see. For instance, this part has in common with the triangle a side. How many such?
3.
Loud, please.
3.
Good. But there are still another kind. This one has in common the triangle just a point, or if you wish to see a vertex. How many such?
3.
3 again. Now, 1 plus 3 plus 3 makes 7. And that's an easier way to count, you see. I hope we can imitate it in space. That was really your idea. Very good. So he was a jump ahead of all of us. Well, so let me repeat the question. We have 4 planes, including a finite solid, a tetrahedron. And they cut space in several pieces. The inside of the tetrahedron is one of them, especially important. This is the only finite one. All the others are around, you see, and we have to count them, you see. And one of you had already the good idea. I just tried to bring up everybody to the same point, you see, how to count them. So, analogously to the case in the plane, also here, finite part, finite, so analogy between the plane, this figure, and space, that figure. Finite part in both cases. Now how many? Here, 1, the triangle. And there, the tetrahedron, that is just
1.
just 1. So finite is just one. But as in the plane case, all the others are around it, have something common with it. For instance, there are some having with it a face in common. For instance, this one, you see. I go through the whole, a face in common. A face. Such a triangle. A face. How many such? 4. 4. Well, even without looking at the figure, I can see you that you are right, because I know that a tetrahedron has 4 faces. But some others has less in common, just an edge, see, just an edge. So an infinite part like that, you see, between, you see, infinite part like that is wedge shape, has such a cutting edge here around. How many such? 6. Very good. So having an edge in common, there are 6. And there is one more case. If it's less than an edge, just a point in common, just a point in common. Oh, these are very well marked. You see, these are emphasized in the figure. There is one I can peek into it from below. I can peek in from it from above. So how many such? 4. 4. And I think that's all a vertex in common. Now, how many altogether? 1, I am quite excited, aren't you? 1 plus 4, 5, plus 6, 11, plus 4?
15.
15? But you told me 16.
Yeah.
So what about the 16?
I think maybe this is a special case.
What?
Maybe this is a special case because 3 of the planes have a point in common.
No. Well, you are right. You should always doubt. But I think that is the general case issue. If you, a special case, for instance, when 2 planes are parallel and is changed ever so little, you see, if the one plane is tilted ever so little, there is an intersection somewhere. But this is a pretty robust case. If you change the faces with quite big angle, no change. Well, yes, yes, please.
The case we did before when we thought it was 16 was
Which
when,
case have we had before?
well, on the board when you had represented the planes by those lines, and you had the 4th plane represented by the
This is
blackboard.
about lines, you see. This is about lines in a plane.
But in the first case, you represented a plane by one of those lines, and the plane was coming out from the blackboard. And you represented 3 planes by those 3 lines, and they were coming out like this.
Oh, from the blackboard. Oh, that was also a pretty general case. You see, if you change any directions, it has. You are right. You should always doubt. Don't believe anything. But I think it is. It looks to me a general case. Doesn't it to you? Yes. What is your?
I think it would have 16 parts if all planes intersected at one common point.
At one point, no, it would have even less. I guess so. That is a very special case. You see, that's 3 planes intersect in one point, but that the force should pass just through that point. Very special case. It is a little more difficult. We don't have, but I can assure you there are still less fast pieces. Yes?
If the new plane cuts all the old pieces in 2, then you have twice as many, and here we're missing.
I didn't quite get that argument.
If the new plane, our speculation was based on the fact that each additional plane would yield twice as many parts as the old case.
Well, that is a speculation. That is,
But-
that's what you guess, that's what you think, but nature is different. So she's like...
Well, that was our speculation, and that would be true if the new plane cut all the old pieces in 2, but it doesn't.
But it does not. That's right. Now we agree. Now we agree. But it does not. Well, look here. It is right. Don't swallow anything easier. it is, I think, it is an experience. 16, that was a respectable guess. It was an inductive guess, not a wild guess. It was a reasonable guess, an inductive guess. Observe the K 1, 2, 4, 8. It was an obvious regularity and was a natural generalization to think it's 16. But you see, the experience which I wanted to give you, if any of you will be a teacher, give it to your students, it is the following, that just such a reasonable, respectable guess may be wrong. And that's it. See? That's all. Such is life. It is wrong. 15 is right. So 15 is right. I have to erase it, but I hope it is not erased in your memory. There should stay a reasonable guess, may come out wrong. Well, but I think we learned something. For instance, an interesting thing we learned is analogy. Without analogy, which one of you very cleverly sensed right at the beginning, you see, without analogy, it would have been much harder to find the number 15. It would have been much harder to find the number 15. Then, another interesting case is extreme case. You can even combine both, you see. We first just divided space by planes. Then we divided plane by lines. This was an analogous case. Let us work it a little more. If you have the plane, if you have one dividing line, then you have two parts. Good. If you have two dividing lines, 4. If you have no dividing lines, how many parts? One. There's just one plane. If you have 3 dividing lines, how many parts? Cannot you look at the blackboard? So how many? 7. Well, but we could go farther. Space divided by planes. Plane divided by lines. What comes after that?
Lines.
Yes?
Well, in space you have 3 dimensions, so it works up to 2 cubed, which is 8, but at 2 to the 4th it doesn't work. And in the plane you have 2 dimensions, so it falls down at 2 to the cube, 2 cubed.
Good, that's a clever conjecture. Very good. Very clever conjecture. Yes, very clever conjecture. He says it goes to the 3rd power because that is space is 3-dimensional. Here goes the 2nd power because that is 2-dimensional. Very clever. But I asked really something very, thank you for the reminder. I asked something else. You see, I asked space divided by planes. This was the first kind of question. Plane divided by lines. What next?
Line divided by point.
Line divided by points. Line divided by points. Oh, that is so much simpler, you see. Here is the line. If there is no dividing point, then there is just one line. If there is one dividing point, how many pieces? 2. Quite clear. If you have 2 dividing points, how many pieces?
3.
If I have 3 dividing points, 1, 2, 3. Now, how many pieces? 4. How would it be with 4 dividing points?
5.
And so on. You are courageous. If it would have any dividing points, how many pieces?
And
plus 1. You see, that should give you, if you are inclined to do something in research, ever, this should give you an ambitious question, you see. Here, you got a formula. What you should have, a formula here. What happens if n lines divide the plane? What happens if n planes divide the space? This is an ambitious plan. And you should be ambitious. If you are not ambitious, you won't get far. should be ambitious in science, otherwise not so good. But in science you should be ambitious. Now, we have little time, so I would be quite happy if you would solve my original question, which was, if you have 5 dividing planes, then space is cut into how many parts? Which number should come here? And we worked so much, we collected some results, and you see, you had a good, you see, his remark was very good. So here, 1, 2, 4, 8, but that is the third power, space is 3-dimensional, the fourth power doesn't work, falls down 1. Here, 1, 2, 4, plane is 2-dimensional, the third power doesn't work, falls down 1. Line is how many dimensional? 1. 1, 0, 1, 2 is already too high, doesn't work anymore. You see, so it's a clever guess. So this number, there is something in these numbers. Now, who can, this is a challenge to your guessing faculty. You see. What should I write here? Looking at this table, what should I write here? A reasonable guess.
29.
What?
29.
29, you say. 29. Perhaps.
28.
Who? Somebody says. Who
28.
Says 20? You say 20.
28.
20. 28. Now I'm short of place.
21.
21. Well, so it's that first to start on the top. 21. I don't know how, what do you say?
26.
You say 26. So very different. Now let me take the last one. How do you come to 26? Could you explain your reasons for 26?
Yeah.
Yes.
I was looking for a pattern in the numbers that are on the board, and I found that if you were working in the third column, that if you took the 2 preceding numbers in the other 2 columns, in that column, to get 8, you add the 2 4s on the 2
for instance,
columns.
you take 4. You see, you take 4. Well, perhaps, or in this column. What's the, yes?
Well, to get the 8 in the
To
third
get the
column.
8, very
Okay.
good.
I added
That is the third row for me. Okay.
That's
so
right, the third row.
8. So you
Yeah.
get the 2 preceding.
Yes, the 4s and the 4. Okay, and to get
And-
that second 4,
Then 8 mixed 8. Good.
and to get
How
that
do you get
second
the 7?
okay, you add the number above it and the 1
4
over
and
3.
3. Okay. And how can the 4?
The 2 2s.
2 and 2 and 4. 2 and 2. 1 and 1. 2, 1 and 1. Hey, seems to go. And 15, how do you get that?
Okay, you add 8 and 7.
Good. So, that is the pattern he discovered. Now, how did he get 26? Anybody else? Anybody follows? Yes?
Add the 7 and 4 in the second and third columns to get 11.
7 and 4, if the pattern continues, then it gets you 11,
Then
and
add the 15 and the 11 in the first and second column.
then you get 26. Well, you see, this is a reasonable guess. A guess by induction. You see, it is based on observation. On observation of the pattern, it is true, then you must have still the courage to say, and so on. Is it right? You had the courage, that's good for you. You see, you had the courage to say, and so on. It will go on, so also 11 will, 7%, it will go on, and this will be go on. So you had the courage. But tell me, is 11 proved? Yes or no? Proved or not?
No.
No more conviction, you answer so weakly. Is 26 proved, yes or no?
No.
No, that was better. No, you see. But now it's another question. Proved? No, it is not proved. But do you believe it? Do you believe it?
Sort of.
Sort of. That was a very good answer. She's a cautious girl. You must be cautious in life. That's good for you. See? Yes, sort of. You have believe it half and half. Not you believe nothing till it is proved. See, that's right. Is it proved? No. But I will tell you. Here I told you one of the important points is test your guess. This is maybe the most important for a scientist. Test your guess. You have to test your guess. So we guessed 11 and 26. Which is easier to guess, 11 or 26? 11. This is just in the plane. This I can do. In space it's very difficult to go do diagram, but in the plane, well, I have to make one more line, any line, here. Any odd line will do. Okay. So count it. So it was a prediction. She predicted, her method predicted 11. Now, let us go catch her. Should we? Shall we? How many finite parts are there? 3. 1, 2, 3. So finite parts are 3. Finite. I just tried the consonants. Now the infinite parts, that is easy in the plane, they are all around. So I put here my finger and start counting. Where my finger is, that is 1, 2, 3, 4, 5, 6, 7, 8. 3 plus 8 equals 11. So what about the 11? You got out, you see? She got away. So 11 seems to be more than just a fact. Now, I would be interested to know, now what do you think? I am just interested in your opinion. 26 was a guess. It is still a guess. But the situation is a little different. Now we have verified 11, you see. This verification could and perhaps should influence our conviction. So after the verification of 11, do you believe in 26 more or less?
More.
That's right. Yes, I think that's the reasonable opinion, you see. Because if 11 checks, that shows that the underlying pattern has something for us. This gives a little more credit to the underlying pattern, therefore the 26. Moved?
No.
So should you believe it?
No.
Sort of. She said it myself. She was sort of believing. Not completely, because it's not proved, but so we didn't give a mathematical proof. What kind of proof did we give? Something important. Inductive evidence. You see, mathematics is good to teach inductive evidence, and that's important. Everything serious that we learn is based on inductive evidence, but even that you can best learn on mathematics. So 26 is not proved. Well, if you work on it a little more, it can be proved, but that we cannot do here. You see, for us, the most important point was I wanted to tell you what is important in reasonable guessing. It is good to look at extreme cases. It is good to look at analogy. Induction is very important. You have to observe. You have to look at the world if you wish to see how it is. But just looking at it, and it is not enough. It is a valuable result if you detect a pattern, you see. If you detect a pattern in the behavior of your boyfriend, that's maybe very important, you see. So detect a pattern. And then you have still the courage to say, and so on. The generalization, the pattern will go on. And all together is induction. But perhaps the most important part is to test your guess, you see. This is the difference between a savage and the scientist, you see. A savage believes his guess, or don't believe it. A savage belief and disbelief. A scientist sort of believes all the time, never completely. Everything could be changed, but some guesses are more respectable than the others because they are better verified. So you have always think of testing your guess. Now I wish to tell you a last story that you shouldn't forget that. So you have to test your guesses and keep always an important difference. This is a fact, this is a guess. this distinction should be very clear in your mind. And the story is just about that. Who should know this difference? A scientist. If he's in England, a member of the Royal Society. All the senior scientists in England are members of the Royal Society. And once a janitor in the building of the Royal Society also made this distinction between fact and the theory, between a fact and the guess. Well, it was so that Sir John, who is a member of the Royal Society, came to a meeting a little late. He was in a hurry, but he had to give his hat in the cloakroom and get a check for it with a number, and he was in a hurry. Then the man in the cloakroom, he was just a janitor, just on duty on that day, noticed that he is in a hurry and said, "Please, sir, you go ahead. You just go ahead. I will give you a hat without a check." So Sir John went thankfully into the meeting, but he had first misgivings. What will happen to his hat? So, however, as he came back, the man in the cloakroom gave him his crack right again. Now, I don't know what happened to Sir John, but he said, perhaps a little too patronizingly, "Well, how did you know that it is my hat?" And the janitor, he answered very sharply, "Sir, I don't know whether it is your hat. It is the hat you gave me."